All right, Honors Chem, we are going to start a new chapter today. And this chapter is called Solutions, but I would really like to say it's going to be more about solutions and mixtures. So if you want to put mixtures on the top, you can. Okay, so solutions and mixtures. If you remember way back at the beginning of the year, we talked about classification and matter, and we talked about solutions and mixtures being mixtures. We have different types of mixtures. We have solutions where everything is mixed down to the very fine molecule or atom or even ion size, where everything's uniform throughout, or we have mixtures where things aren't uniform throughout. So we're going to do a lot of vocabulary today. We're going to start by defining a few terms. It says this will be done on your own time, but no, we're going to do it right now. If you want to, you can use the internet as well to clarify some definitions if some of my definitions don't make sense to you. So the internet is a great place to go to get some clarification. Okay, so we're going to start with suspension, colloid, and Tyndall effect. So suspensions and colloids actually aren't solutions. They are mixtures that are heterogeneous. So if you remember, these are mixtures that are heterogeneous, which means if they're heterogeneous, they are not uniform throughout. So I'm going to have little chunks of things going through. Now, before we said that a suspension was a heterogeneous mixture where the particles settle out. And by settle out, I mean if I stop agitating, mixing, stirring, shaking in some way, if I let that mixture just sit, the particles will start settling out and going to the bottom. So suspension is a heterogeneous mixture where the particles will settle out. Upon standing. Now, when I mean upon standing, standing is just another way of saying letting that mixture just sit and not be agitated or stirred or shaken in any way. Now, there is a technical definition for a suspension. The particles in a suspension are between 1 to 1,000 nanometers big. That is the technical definition of a suspension. Those are usually particles that are big enough that we can see them with the naked eye. Okay? All right. Our next one, we are going to do colloid. Okay? Now, a colloid is also a heterogeneous mixture. So that is the same heterogeneous mixture. But the particles are small enough that they don't settle out if I stop mixing. These where particles are of intermediate size. So they are larger than a molecule, but they are smaller than 1 nanometer. So they are about 0.1 nanometers to about 1 nanometer is the size of colloids. And these particles will not fall out of solution. So these particles will not settle out. They remain suspended. Okay, so a good example of this is, let's see, like mayonnaise. Mayonnaise is a mixture of oil in water. And because we've whipped that mayonnaise with egg whites become the, egg yolk becomes the emulsifier. which allows the particles of the oil to become so small that when we whip it in there, the particles become so small that it doesn't settle out. Your jar of mayonnaise stays mayonnaise. It doesn't settle out into oil and water. Those particles become so small. So mayonnaise is a great example of a colloid. All right. And then we have an effect that we can use to help us distinguish between a solution, a uniform mixture, and a colloid where the particles don't settle out, but the particles are still so small that we can't see them with the naked eye. It's called the Tyndall effect. Now, the Tyndall effect is named after the Irish chemist Tyndall, and he noticed that when he shined a light through a solution, the light totally wouldn't reflect in the solution. The particles in the solution are so small that the light waves can go around those particles in the solution because they're down to the atomic or the molecular level. But in a colloid, even if we can't see it, in a colloid, we have what we call this. Do you see that light scattering? I should do a different color. Do you see this light scattering in here? That light scattering is because the particles of the colloid are big enough to actually get in the way of the light waves going through that mixture, that it scatters the light all kinds of different directions, and that's why we get this scatter effect. So the Tyndall solution, or the Tyndall effect, is the scattering of light. By larger particles. So we can get the scattering of light in colloids and suspensions. Okay, so if you can't see the particles that are in that mixture, it's really a good idea to just shine a beam of light through that. And if you don't see any of that beam of light in that mixture, you know you've got a solution. But if you get some of this scattering, you can see that beam of light, you know you have a colloid. Okay? So that's a really quick, easy test to distinguish between a solution and a colloid. Okay, we've all seen this. Like if you've opened up the window on a really bright sunny day and that beam of light's coming through, you can see the dust floating around in the air. That's the Tyndall effect. Okay, all right, some more definitions. So we've all heard of these words before, but we probably don't know that there's actually a technical definition. It looks like I'm missing some stuff. Nope. Okay, here we go. Foam. In a foam, we have foam is a suspension of air, of either a solid or a liquid in a gas. A suspension, sometimes it can be colloid, of a solid or liquid in a gas. Okay, so a good example of foam would be styrofoam. Right, we've got styrene with that gas that makes it all puffed up, which makes it a really good insulator. We have shaving cream. We have the liquid of the shaving cream suspended in that gas, that foamy stuff for shaving cream. Okay, Aerosol is a suspension of a liquid or a solid, also in gas, but usually we have much more of a gas mixture. So this foam, we could actually say a suspension of a gas in solid or liquid, because the majority of this is either a solid or liquid. Aerosol, the majority is gas. A suspension of a solid or liquid in a gas. Okay, so aerosol, a lot of our cleaners are aerosols. We have cans of like window cleaner where we have a liquid that's propelled by gas to come out of that can. We have deodorant, that's an aerosol spray. We have perfume a lot of times, that's an aerosol. We have a liquid that's propelled by gas. So I'm trying to think of a solid example of an aerosol. A solid example of an aerosol would probably be smoke. So smoke would be a good example of a solid, the ash suspended in the gas. Or perfume would be a good liquid suspended. A lot of our cleaners are this way. Okay. A sol is a solid suspended in a liquid. And it's a suspension. So it will settle out over time. A suspension of a solid in a liquid. So a good example of this is paint. If you've ever had a can of paint that sat around for a good long time, you'll notice that the color actually kind of falls to the bottom. And you have to re-stir it up or shake it up because that color is little solid particles that are suspended in a liquid latex usually. Most people use a latex paint. Another good example of a sol is if you've ever done artwork with India ink. India ink is little tiny black solid particles that are suspended in water. And if you let India ink sit for a long time, those particles will fall to the bottom and you have to re-stir it or re-shake up the India ink as well. Okay. Emulsion is a colloidal suspension. Oh, I can't spell. So emulsion is a colloidal suspension of a liquid in another liquid. And usually we make little tiny particles, little tiny packets that are so small that it stays colloidal, so it doesn't really separate. So a really good example of a colloidal suspension or an emulsion is lotion. So if I have lotion, I usually have some kind of oil that has been whipped into water. Okay, so that's a really good colloidal suspension. Another colloidal suspension or emulsion that you would think of is chocolate milk. If you've ever gotten a can or a bottle of chocolate milk and it sat for a while, it does tend to fall out. You'll see a lot more chocolate at the bottom, so you have to kind of shake it up because the liquid chocolate fat globules will fall out of that suspension every once in a while. So, and we have to shake it up every once in a while to keep it going. Okay, we have solutions. Solutions are homogeneous, so they are uniform throughout. So very different than what we've been doing. These are homogeneous, so that means that they are uniform throughout. Okay, so these are uniformly distributed throughout. The mixture. Okay, so it's not going to be more concentrated in one part than another. So we are down to the atomic, the molecular, or even the ionic level. Okay, so we have individual molecules, individual atoms, or sometimes even individual ions. So we're down to the smallest particle that we can possibly have and still have the thing that we're talking about mixing in. Okay, so let's see what else I wanted to do. So it's uniformly distributed throughout. Okay, solute. Let's do the definition of solute. So solute is the thing that is dissolved. The thing or the substance that gets dissolved. So when we're talking, for example, of putting some salt in water and making salt water, the solute would be the NaCl. Okay, that is the stuff that gets dissolved. We a lot of times think of it as a minority or a majority portion. So the solute is the minority portion. It's the smaller of whatever the mixture is. It's the minority portion. Okay? So the solvent then is the substance that dissolves the solute. I can't spell. Substance that dissolves the solute. So in our example up here, water would be the solvent. Okay, so it is the majority portion. Okay, and then the last thing one of the last things I want to define is an alloy. So an alloy is a solution. It's a solution, so it's a uniform mixture of two or more metals. Sometimes it's not even a metal. Sometimes we will actually put carbon in there with metal. So it's a solution with metals or other things in that metal that are uniformly distributed. Okay? So I wanted to talk about examples of solutions because a lot of times when we think of solutions, we think that solutions have to have a liquid involved. Obviously, alloys are metals. Metals aren't necessarily liquids at room temperature, so that blows a hole in that theory. So here we go. Here's some examples. I'm going to blow this up really quick. So I can have a solution that is made just of gas. Air is a great example of a solution that's made just with gas. Its majority portion is nitrogen, and its minority portion is oxygen, carbon dioxide, argon, and a bunch of other trace gases. But because the gas molecules are so small and travel so quickly and travel so randomly, it is a solution. It is uniformly distributed. Okay? Liquid. I can have a water gas mixture, or carbonated water or soda pop is that way. I have the liquid water being the solvent, and I have the carbon dioxide or the bubbles being the gas. And the bubbles just get released as we release the pressure of the can by opening up the can or opening up the bottle. I can have a solid liquid solution like ocean water. I have a liquid solvent, and I have the salt being the solid, or I could have the gas. I could also have it look at it as a gas with the oxygen gas dissolved. And that oxygen gas dissolved is what the fish breathe down there. Okay? I could have antifreeze that we use in our car. I've got liquid mixed with ethylene glycol, so I have a liquid-liquid mixture. Vinegar is a liquid, acetic acid liquid mixture. So ocean water, liquid solid water with the sodium chloride, which is solid. I can have a solid-solid mixture. So the old-fashioned dental fillings that are silver, this is called dental amalgam. It was mostly silver, but it was mixed with mercury to make it soft enough so that the dentist could put it in there. That's why we don't do those anymore, because the mercury is kind of toxic. We use porcelain instead. And now we also have steel, which is a nice solution between iron, which is our solid, mixed with carbon, which is also a solid. We also have gold, for example. The gold that we use for jewelry, 14 karat gold, is mixed gold, which is the solvent, with a little bit of silver, which is the solute, to make it a little bit more rigid and a little bit more strong. Okay. We also have brass, which is zinc with copper. We also have bronze which is tin with copper. So we have all kinds of different mixtures going on. It does not have to be a liquid. Okay? So I'm going to put 2 videos on here of ways that we can separate components of a suspension. The first is filtration. And if you ever have a filter at home, a lot of you will have a water filter at home, or if you've ever had like a coffee pot or anything, you have your coffee filter, and we're basing what can pass through based on size. So we're keeping up the big things, we're making a barrier so that the big things get caught behind and the small things can still go through. So it's a method used to separate the components based on size. Okay, so we put a physical barrier to trap the large particles and let the smaller ones through. Okay, that's how a filter works. All right, and sometimes we can also separate based on magnetic attraction. So if I have metals, you've all noticed that some metals are what we call ferromagnetic and able to be attracted to a magnet, and other metals are not what we call ferromagnetic and not attracted to a magnet, like the difference between iron and aluminum. We can separate based on that. We can pass a magnet over something and get all the things that are ferromagnetic out of there and leave the non-ferromagnetic metals behind. So this is a technique used to, there goes this again, it's thinking. Technique used to separate metals based on ferromagnetism. Basically, whether they're magnetic or not. There's another type of magnetism that's called paramagnetism too. Maybe we'll get into that in a bit. We should do that when we do quantum. That's a fun thing to do with quantum. Okay. And we have some methods that we can actually use to separate the components of solution. Distillation is based on separating things based on their different boiling points. So this is a technique used to separate components based on different boiling points. Okay, if you've ever driven up north in northern Salt Lake County to the Bountiful Woods Cross area, over to the west side of I-15, you'll see a whole bunch of oil refineries, and they have a huge towers. If you've ever seen those huge towers, those are distillation towers, and they are using distillation to separate the raw, unrefined oil into its various parts. So they have a tower, and they heat up the raw or the crude oil. And the things that have really high boiling points are going to stay liquid. And these are the heavy, long carbon chain things like the tar and the asphalt things that we use to make our roads. And then in the middle of the chamber where it can get a little bit hotter, we can pull off gasoline. Those are like the medium-sized chain, carbon chains, gasoline, airplane fuel is a little bit longer. And then at the very top, sometimes you'll see a flame on the top. Sometimes you'll see a tube coming off the top if they're actually trapping it. They'll get the methane, which is the shortest hydrocarbon out there. It's just CH4. It's the main component in natural gas. And so they will heat that up, and as to the boiling points, as they become gas, they will pull them off at different levels of the tower based on the different heat points, and they can separate out the raw materials of the raw crude oil and make all the various things that we need with distillation. We can do that also. A lot of people will distill different alcohols. They'll distill drugs this way by pulling things out by different boiling points. I'm going to put a video of distillation on this so that you can see what that is. Chromatography. Chromatography is separating things out based on their affinity or their attraction to what we call a solid phase versus a wet phase. Okay, so let me draw this out. Let's put the definition first, and then I'll draw out how this works. So this is a technique to separate components based on their affinity. And affinity is just a fancy word for attraction to, based on their affinity to a solid phase versus their affinity to the liquid phase. It also separates based on size. Size is a big factor here too. Okay, so if you've ever colored something with magic markers, especially if the magic markers are water-based markers, and you've accidentally spilled water on a corner and the water has traveled through that paper a little bit, and you kind of get the marker to be, it kind of discolors. Sometimes the marker will travel with the water in the paper. You've seen chromatography. So on chromatography, what we will do is we will take a little bit of something, put it on some really thick, what we call filter paper, and we will dip the bottom end of the filter paper in some kind of solution. Sometimes we will use a solution of water. Sometimes we will use a solution of alcohol, maybe even turpentine or something. And we will put it up in a beaker and we will wait for that solution to travel up the paper. And as that solution travels up the paper, the various components in this little dot that we put on the paper, some of them will like to travel with the solution. Some of them will be really big molecules that will kind of get stuck on the paper and have a harder time traveling. Some of the components will actually be more attracted to the paper than they are the solution. So given time, we will have different components coming out at different levels on the paper. So we will separate those components based on, one, how attracted they are to that liquid or that solution phase. Two, how attracted they are to the paper. The more attracted they are to the paper, the less they're going to move. The more attracted they are to the solution paper or the solution, the more they will move with the solution. And another thing is size. The bigger the molecule, the harder it is to move through that paper. Okay, right? It's a lot harder to move a 300-pound person than it is to move a 50-pound person, right? So we are separating things based on affinity to the solid, the paper, or affinity to the solution, or size. So we really get a pretty good separation. And I'm going to show you a good video of that. I love doing chromatography. I've done a lot of chromatography. Okay, so that is the definitions of things that I want you to do. Now, next time we're going to talk about why things dissolve in other things. We're going to talk about why some solutes dissolve in particular solvents and why others don't. And we're going to start talking about the reasons behind that. So have a great day. We'll talk to you later. Bye.